Welcome back. In this video, we continue learning about the buck converter. Previously, we introduced DC-DC converters and derived a mathematical model for the switch mode currents and voltages. In this video, we will develop an approximate method to solve the inductor current by assuming that the output voltage is constant. Using the same approach, we will also derive equations to approximate the cyclic variation of the output voltage. Next, we will define and discuss the possible modes of operation, namely continuous conduction mode, borderline conduction mode, and discontinuous conduction mode. Finally, we will give an example of a real-world application of buck converters. As discussed in the previous video, the exact analytical solutions for current and voltage waveforms are complicated and mostly solved numerically. However, the solution can be approximated with very simple analytical equations. Remember the circuit diagram of the buck converter? In order to create a smooth current and voltage at the output, the buck converter has a low-pass filter comprising an inductor and capacitor. If we assume that we have an ideal low-pass filter, then the output voltage will stay constant. Or, in other words, we use a very large capacitor so that there is no variation on the output voltage waveform. Therefore, we can use a circuit diagram shown here, where the output becomes a DC voltage. The assumption that the output voltage is constant is reasonable as long as the cutoff frequency of the filter is much lower than the switching frequency. We will elaborate more on this later in the video. By assuming a constant output voltage, we can derive simple equations for the currents and voltages in the circuit. This is a plot of the voltage across the diode. As we can observe, the voltage is equal to the input voltage when the switch is on and is equal to 0 when the switch is off. Shown on the same plot is the output voltage, which has a constant value. It is obvious that the output voltage will always be less than the input voltage in this buck or step-down converter. We will now derive the equations for this output voltage. The buck converter has two possible states, one with a switch on and the other with a switch off. In our new diagram, when the switch is on, the circuit is equivalent to this. And when the switch is off, the circuit looks like this. When the switch is on, the voltage across the inductor is the difference between the input and the output voltage. By integrating the inductor voltage over time, we can solve for the output current. Since the output voltage is greater than the input voltage, the current is increasing linearly. When the switch is off, the voltage across the inductor is simply the negative value of the output voltage. We can again solve for the output current, and we find that it is decreasing linearly. We now perform a quasi-steady state analysis. Quasi-steady state means that all the currents and voltages at the end of the period are exactly the same as at the beginning of the period. Here we observe a plot of the current flowing into the inductor and the voltage across the inductor when it is in quasi-steady state. The current at the end of the period must be equal to the current in the beginning. Because the current in an inductor is given by the integral of the voltage, we can conclude that the integral of the voltage over a single period must be 0. In a graphic interpretation, this implies that the surface underneath the voltage curve when the switch is on must be equal to the area when the switch is off and the diode conducts. So we can set these areas equal to each other and calculate the output voltage. When solving this equation, we find that the output voltage is equal to the input voltage multiplied by the duty cycle D. The duty cycle is defined as the switching on time divided by the switching period. In other words, it is a fraction of time when the switch is on. Since we can freely control the on-off ratio of the switch, we now have a straightforward method to adjust the output voltage. Notice that since the value of D varies between 0 and 1, it is demonstrated mathematically that the output voltage of the buck converter will always be smaller than the input voltage. Next, we calculate the output current. In an ideal circuit, there is no energy lost, implying that the power that goes into the buck converter is equal to the power that comes out. Since the power is current multiplied by voltage, we can determine that the ratio of the output to the input current must be 1 divided by D. In the first step, we approximated the operation of the buck converter by assuming a constant voltage at the output. Now we assume a constant current at the output. This allows us to estimate the cyclic variation of the output voltage, known as the voltage ripple. Note that these approximations only work if the ripple of the output voltage and the output current are small. In this circuit, the capacitor current is given by the difference between the inductor current and the output current to the resistor. So we use our previous approximation of the quasi-steady state current to calculate the approximate current in the capacitor now. Also, in quasi-state operation, the average capacitor current must be equal to 0. The change in the voltage across the capacitor is given by the integral of the current divided by the capacitance. In other words, the charge that flows in and out of the capacitor. This charge can be represented graphically as the area of this triangle. So we can use straightforward geometry principles to calculate the area of this triangle. We will not do a step-by-step derivation here. You may verify it yourself. The final value for the voltage ripple is given by the equation here. The voltage ripple is a function of the switching frequency, the duty cycle, the inductance, and the capacitance. Do observe that the voltage ripple becomes small when we reduce the duration of the switching period, implying a high switching frequency. The ripple also becomes smaller if the inductance and/or the capacitance is increased. We can also express the voltage ripple in terms of the cutoff frequency of the low-pass filter given by F subscript C. The value is a function of the inductance and capacitance. As we can observe from the equation, if the cutoff frequency of the filter is significantly smaller than the switching frequency, the voltage ripple becomes also very small. This is because of a proportionality equal to the square of the ratio of these two frequencies. This means that our assumption of a constant output voltage should be very reasonable. This assumption, however, relies on the converter operating in continuous conduction mode. Here is a graph of the current in the inductor. As you can see, the current rises and falls linearly around a certain average value. Yet, the inductor is always conducting current. This state is called continuous conduction mode. In the buck converter, we have a resistor as a load. And according to Ohm's law, if we increase the resistance, the output current will decrease. When the resistance is increased to a specific value, the inductor current will just touch the horizontal axis. This operating point is called borderline conduction mode. If we increase the resistance even further, the average current will decrease even more. However, in this circuit, the inductor current cannot go negative due to the polarity of the switch and the diode. Consequently, the inductor current stays zero for an interval during the period. This is the discontinuous conduction mode. Discontinuous conduction mode requires a different set of equations for the voltage and current, and we will discuss it in a later video. So why do we need buck converters? Well, buck converters convert DC power from a high voltage level to a lower controllable voltage. For example, in a laptop, any computer, and even smartphones, we need a low voltage for the microprocessors and other digital circuits. The voltage typically varies between 2 and 5 volts, and the value is actively regulated to improve the efficiency of the information processing. So this is one of many applications. Maybe you could use internet and see what other applications you can find yourself. To recap, in this video we introduced modifications to the circuit of the buck converter so that we can derive the describing functions. We first assumed that the output voltage is constant. Then we derived the equation for the inductor current, which was used in a second step to calculate the voltage ripple in the buck converter in continuous conduction mode. After that, we discussed the differences between continuous, borderline, and discontinuous conduction modes. And finally, we discussed one important application of the buck converter, namely the power supply for digital circuits. What do we do when we need to step up or boost the source voltage? We now move in the next video to a DC converter circuit that's able to increase the source voltage to a higher level. Thank you for watching.